Welcome all of you to the chemistry online classes. Today we are going to discuss about the that is CFT, crystal field theory. So this theory was proposed by the scientists Bethe and Van Vleck. Okay, and they have given certain features regarding the crystal field theory. What exactly it says? It's like first feature is the coordination compound is considered as an electrostatic model. Here this is the coordination complex or the compound is considered as an electrostatic model where the metal ligand bond is ionic. So according to this theory, in case of electrostatic model, it is the coordination compound is considered as a electrostatic model, and here in between the metal and ligand the ionic bond is present. Okay. And then the negatively charged ligand considered as a point negative charge. The negatively charged ligand considered as a point negative charge, whereas the neutral ligand considered as a polar molecule. So as you know, polar molecule, one will be the positive end, one more will be the negative end. So the neutral molecule is considered as a polar molecule, while the negative charged ligand is considered as a point negative charge. Negative is considered itself as a negative. Clear? Next one is here. Suppose the central metal atom attracts the negative electron cloud of the anionic ligand or the negative end of the dipolar ligand molecule. See here, the ligand may be negative. Okay, the ligand may be, according to this point, we have the central metal atom and the ligand. This is the ligand. The ligand may be negatively charged or neutral. Yes or no? The ligand may be negatively charged or neutral. Suppose if it is a negative, it is considered as a negative point only. If it is neutral, its negative end is considered. According to this point, if the neutral ligand is there, it is act as a polar molecule. It means two ends will be there. One is positive end, one more is negative end. Okay, this point, the central metal atom attracts the negative electron cloud of the anionic ligand. Suppose if it is an anionic ligand, the metal, this central metal attracts the negative electron cloud of that one. If it is neutral, during that time the negative end of the dipolar ligand is considered. Here, during when it is neutral, the negative end is attracted towards the central metal atom. And the last point is the ligands are arranged around the central metal atom in such a way that the repulsion between the negative points is minimum. The ligands are surrounding the central metal atom in such a way that the repulsion between the negative points must be less or minimum. So all these are the features. Exactly, it is not mentioned in your NCERT. For knowing the theory in a better way, so I have written few of the points referring from other book. So just you remind these all points. No need to, according to your examination point of view, it is not that much. We can say the questions will not going to be asked on this concept, but whatever now I am going to explain, that will be definitely asked in your examination. So this is the brief introduction of the crystal field theory. Okay, so now let us go for the exactly what is crystal field theory, what it says, and how the ligand approaches the metal atom, and what happens inside the orbitals of the metal. Clear? So see here, d orbital. Five d orbitals are there. Yes or no? That is dxy, dyz, dzx, dx square minus y square, and dz square. 5 d orbitals will be there, and these are called as degenerate d orbitals of metal. That is, central metal atom has a 5 degenerate d orbitals. Okay, and these 5 degenerate d orbitals. Degenerate is nothing but these all orbitals are having the same energy. All the orbitals are having the same energy. Clear? And here in this 5 orbitals dxy, dyz and dzx. These are the 3 orbitals where the lobes are present in between. Here the lobes of the orbitals are present between the axes. Between the axes. For example, suppose this is x and this is y, and the lobes are present in between the axes like this. These are nothing but dxy, dyz, dzx. These are the 3 orbitals where the lobes are present in between the axes, and this orbital is said to be, according to the spectroscopy, this is the new term for you people, according to the spectroscopy, this is called as T2z orbital. Okay, T2z includes the 3 orbitals which are those dxy, dyz and dzx. Clear? And what about other 2d orbital? Other 2d orbitals are nothing but dx square minus y square and dz square. See here, dx square minus y square and dz square. Here the lobes are present. Here the lobes of orbitals are present along the axis. Along the axis, and according to the spectroscopy, this is easy orbital. This is easy orbital. Are you getting? See here, 5 d orbitals will be there, and these d orbitals are said to be degenerate d orbitals of the metal. Degenerate in the sense those are having the same energy. All dxy, dyz, dzx, dx square minus y square, dz square, 5 orbitals are having the same energy. In that 5, we are going to see here dxy, dyz, dzx. Here the lobes of the orbitals are present between the axes, and this is termed as a T2z. How to pronounce it? T2z orbital according to the spectroscopy. Okay, and then here 2 more d orbitals are there. Those are dx square minus y square and dz square. These are here. In case of these orbitals, the lobes are present along the axis. The lobes are present along the axis, and these are nothing but easy orbital. So easy and T2z are the terms. Easy and T2z are the terms referred with the help of the spectroscopy. Spectroscopy, it is also a branch of chemistry. Okay. So you need to remember this. T2z means it consisting of the dxy, dyz and dzx. Easy means it consisting of the dx square minus y square and dz square. Okay. Now any complex is there. Any complex is how it is formed with the help of the ligand. Only now we are talking about the central metal atom. We even want the ligand. So when the ligand approaches the central metal atom, when the ligand approaches the central metal atom, there is a repulsion between the ligand and these orbitals of the metal. Why there is a repulsion? Because the ligand also consisting of lone pair of electron. Even the central metal atom d orbital also consisting of the pair of electrons. So both are electron means there will be a repulsion. So when the repulsion occurs, the degeneracy of d orbital will be lost. Okay, degeneracy lost in the sense these all d orbitals does not have the same energy, those are having the different energy. When it happens, when the ligand starts to approach towards the central metal atom, Why? Because there is a repulsion occurs between the electrons of the ligand and the electrons of the metal. So what happens here? This is the d orbital, which is a degenerated d orbital first. Degenerated d orbital. Okay, and then whenever, and these are dxy, dy, dz square, as I said you. Now, when the ligand wants to approach these orbitals, there is a repulsion between the ligand and these orbital because of the electron. During that time, the degeneracy is lost. So what happens here? These are there is a formation of the non-degenerate orbitals. These are non-degenerate orbitals, or these are also called as average energy of d orbital in spherically crystal field. Okay, these are the non-degenerate d orbitals. It means now these d orbitals does not have the same energy, So what happens during this time, when the ligand starts to approach it, there is a splitting of these degenerate orbitals will going to be takes place. There is a splitting of the splitting. Okay, now you know this consisting of the T2z as well as EZ. There is a splitting of these non-degenerate orbitals due to the influence of the what? Due to the influence of the ligand. It will going to split up. Into two sets of the orbitals. One set will be one set here, one set orbital, and here another set orbital. This is nothing but crystal field splitting. So what is crystal field splitting? The splitting of the non-degenerate d orbitals with the influence of the ligand to give a definite geometry. That is nothing but crystal field splitting. Crystal field splitting. And then this is whatever the energy difference between these two sets, this is nothing but crystal field splitting energy. That is indicated by the term, it is represented by the delta. One term you need to know what is crystal field splitting, and one more is crystal field splitting energy or crystal field stabilization energy. See here, what is crystal field splitting? The splitting of the non-degenerate orbitals with the influence of the ligand to give a definite geometry. That is crystal field splitting. And what about crystal field splitting energy? It is the energy difference between the that what we can say orbitals. The energy difference between the orbitals is nothing but a crystal field splitting energy or crystal field stabilization energy. I hope so it is clear for you. Now there is a one question arises. This non-degenerated d orbitals means it may be dxy, it will be a dxy, dyz, dzx, dx square minus y square and dz square. In that these are T2z, and while these two are the EZ level. So which level will come upside, which level will come downside? That is the question. So this will be different in case of the octahedral ligand and in case of the tetrahedral field splitting. Okay. So we will discuss about, first we are going to discuss about the octahedral, then we will go for the tetrahedral. This crystal field theory in case of the octahedral crystal field. It means octahedral means like Ml6, the ligands will be like COF6 or COCN6 like this. It means the ligand must be 6, that is octahedral. So whenever the octahedral will be there, that is the d orbital splitting in an octahedral crystal field, how it will going to split up. See here, first these are the degenerate d orbitals of metal. Okay. So when the ligand approaches, what happens? The degeneracy is lost. So here these are non-degenerate, or you can write the same thing, average energy of d orbitals in the spherically. I will write shortly, okay, but you don't go for like this. Simply I have written completely there, that's why I am short. I am doing here short. D orbitals in spherical crystal field. Okay, same thing. Now the ligand approaches, which type of the ligand? 6, it means octahedral field. In the octahedral crystal field, what happens? The splitting of this degenerate orbitals will going to be takes place, or you can take like this, no problem. So here this is easy level. Which are the orbitals here? dx square minus y square and dz square. This is dxy, dyz and dzx. This is T2z level. In case of octahedral crystal field, the ligand approaches along the axis. So which orbital is lying along the axis? Easy. So it is raised. So that orbital is raised. Easy comes in the upper side. See here, in case of octahedral crystal field, the ligand approaches along the axis. See here, along the axis, which orbital is there? Easy orbital is there. So easy will be raised. So first easy will come up. While what about T2z orbitals? The T2z orbitals are, the lobes are present in between the axis. So the less repulsion will be there. So it will be in the downside. Okay. So now this splitting is nothing but crystal field splitting. Okay. And what is crystal field splitting? The splitting of the average d orbitals, average energy d orbitals in a spherical crystal field with the influence of the ligand, because ligand approaches with the influence of the ligand to give a definite geometry. And this is nothing but crystal field splitting energy. How it is represented? Delta. And it is the octahedral crystal field we are discussing. So I will write here a delta naught. O indicates octahedral. O indicates octahedral. So now what is that? One more thing. And this is the crystal field splitting energy. The crystal field splitting energy means the energy difference between T2z and EZ, or these two EZ and T2z orbitals is nothing but we can say the crystal field splitting energy or crystal field stabilization energy. And then here the energy of only EZ will be, that is 3/5 delta naught. It is a 3/5 delta naught. It means in the 3 here this EZ, this energy, this only up to this energy is 3/5, and here it is a, that is T2z, that we are going to crystal field energy is 2 by phi delta naught, and here it is decreasing, so we can take minus sign, here it is increasing, we can take the plus sign. In some books they will mention plus or plus and minus signs also. In some books they will not going to mention about the sign, only they will give the explanation about this value. So, what about the crystal field energy for the easy level? That is 3 by 5 delta naught. If you calculate, it will be around 0.6 delta naught, I hope so. Okay. And then that is the crystal field splitting energy for the T2z level is, that is 2 by 5 delta naught, which is equals to 0.4 delta naught. And even it can be expressed in terms of dq, it will be a 10 dq, total delta naught value, that is delta crystal field energy in case of octahedral will be 10 dq. So, this is how the crystal field splitting takes place when we have the octahedral crystal field. And then if it is a tetrahedral, that will be a different. If it is a tetrahedral, that will be a different. So, once again I will explain you. First, the metal has a d orbitals. First, the metal has the d orbitals. These are the 5d orbitals. These are the 5d orbitals, and these are the degenerated d orbitals of the metal. What is the meaning of degenerate? Same energy. Okay. So, now in these 5 orbitals, the dxy, dy's, dzx, the lobes of these 3 orbitals are present between the axes. So, these are considered as a T2z orbitals according to the spectroscopy. The spectroscopy has given that term T2z, and then dx square minus y square and dz square, here the lobes of the orbitals are present along the axis. Along the axis these are present, this is referred as easy orbital. Clear? So, now when the ligand approaches the central metal atom, during that time there is a repulsion between the ligand and this d orbital, because this metal orbital also, this d orbital of the metal also consisting of electron, and the ligand itself has a lone pair of electron. So, there is a repulsion. During that time the degeneracy is lost. So, there is a formation of the non-degenerate orbitals. Okay. And when the ligand completely approaches it, there is a splitting of this orbital will going to be takes place. That splitting is what we called as crystal field splitting, and the energy difference between those 2 orbitals is nothing but crystal field splitting energy or crystal field stabilization energy, that is shortly written as a CFSE, crystal field stabilization energy or crystal field splitting energy. Okay. So, now we will discuss this crystal field splitting energy or that crystal field splitting in case of an octahedral crystal field. Octahedral complex is there means during that time. So, these are the degenerate d orbitals and this is a non-degenerate d orbitals when the field is octahedral. So, what happens? This will going to split in such a way, the ligand approaches along the axis, the ligand approaches along the axis. So, the easy level will be more repelled and it is raised, and it is raised, so easy will be upside. You can ask me why not T2z is upside. This is the reason. The ligand in case of the octahedral crystal field approaches along the axis, so the easy level is raised up, while T2z is in between the axis, that is a downside. And here this is nothing but a crystal field energy, crystal field splitting energy, that is indicated by delta, and this O indicates it is octahedral crystal field. And then here the easy, the CFSE value for the easy will be 3 by 5 delta naught, that is delta in the octahedral field, that is exactly 3 by 5, that is 0.6 its value will be, and in case of the CFSE of T2z orbital will be 2 by 5 delta octahedral field, that is 0.4 delta naught we can able to say. Suppose if it is instead of octahedral, if it is tetrahedral, during that time it will be exactly reverse. T2z will be upside, EZ will be downside. That I will explain you in your next class. Until that, keep watching the video and note on all the points. Okay, thank you.